All right, we've explained to you what do we mean by molarity. We did some brief examples of calculations, the type of calculations that you might see. We showed you how to make a dilution and so forth. Now we need to apply some of that information to a little bit more in detail when we go look at chemical reactions. All right, so all right. That's what this statement says. So in reactions involving solutions, right? Normally you can make a reaction by adding dried stuff, but let's say you have solutions containing your reaction components. You want to mix those together. Okay? In the past, we're dealing with this grams to moles and then moles to grams calculation, right? So we had X plus Y going to A plus B, and I said 5 grams of X and 10 grams of Y. How many grams of A and B do we get, right? You have to do the mole conversion. You have to then decide what the limiting reactant is. We're still going to worry about the limiting reactant here. Okay, but now we're going to see volume. In other words, volume to moles and then moles to volumes. And then we could still go to grams if we want to. All right, so here we go. This is sort of a general layout. This is what we were doing before, grams to moles, back and forth. Remember I said probably one of the most common conversion that you'll do in this class is moles to grams, grams to moles. And we use molar mass or formula weight for that. All right. What we're going to be doing in the next set of examples is moles, volume, back and forth, and we use molarity. Molarity, remember capital M meaning moles of solute, liters of solution. Okay. And then stoichiometry is what we use, similar to what we did before, right? We got to do mole ratios. You know, how many moles of these two reactants react? How many moles of the products do we get, and so forth. All right. So best thing to do is just dive in again to show you some examples. Keep in mind that we've got some additional problem-solving videos that you'll find helpful. All right. Here's my first example. By the way, if you see these little pictures of pencils up on the slide, that's to remind me that this is a slide that I need to do some writing on. So it's just for my memory. For the following reaction, what mass of calcium carbonate is required to react with 25 mils of 0.75 molar HCl? Wow. So let's look at the reaction first. All right. Calcium carbonate, notice a solid, okay? HCl, aqueous. So we've got, our question is, I'll put a question mark there with grams. In other words, how many grams of calcium carbonate do we need to react with 25 mils of 0.75 molar HCl? So how do we do that? By the way, the answer's down here, so we'll work through there. Well, let me erase this and just tell you, notice the mole ratio. In other words, whatever we calculate for the moles of HCl, and how do we do that? Well, we're going to use volume and molarity. We only need half that amount for the calcium carbonate, right? Because it's a 1 to 2. So let's calculate how many moles do we have of HCl in that 25 mils. So remember, volume times molarity equals moles. All right, so here we go. 0.025 liters, that's the 25 mils, okay, times 0.750 molar equals, I'll just write down X moles of HCl. Okay. That's how many moles of HCl are in the reaction. Again, the question is asking how many grams of calcium carbonate do we need? Okay. Well, let's go down here. So I'll need X divided by 2 moles of calcium carbonate, right? Because we only need half of that amount, half in terms of moles of the calcium carbonate. So once we have the moles, then we just multiply it times the molar mass. So this is going to be, put this in brackets, times 100.1 grams per mole. If you do that, you should get 0.938 grams of calcium carbonate. So let me just go through that one more time. We need 0.938 grams of this to react with 25 mils of that HCl solution. Okay, remember that's what we say stoichiometric, meaning that's the exact amount of those two things. We could have had excess, but we just pose the question this way. All right, Another one. All right, this is going to be a little bit more difficult. If you mix 20 mils of a 0.4 molar lead nitrate solution and 60 mils of a 0.2 molar, so 20 mils of a 0.4 molar lead nitrate and 60 mils 0.2 molar sodium chloride, how much lead chloride precipitate will you get? This is one of those metathesis reactions, and you're being told that a precipitate is formed, and you're told that it's lead chloride, so that makes life easier. So hint number one is we have to write a balanced equation, and you'll see why that's important. And then hint number two is this turns out to be a limiting reactant problem, so you'll see that. Let me fast forward here to the next slide. So let's write down our equation first. We've got lead nitrate, and we'll do 2, and I'll put the AQ in there, plus, where are we at? Sodium chloride, AQ, and we're going to produce lead chloride, solid, plus sodium nitrate, AQ. All right, to balance this, we need to get everything the same, so we're going to put a 2 here and a 2 here. That's your balance reaction. Why is that important? Well, again, it's because for every 1 mole of lead nitrate, we need to react 2 moles of sodium chloride. All right, what is the net ionic reaction for this? It's going to be lead 2 plus AQ, right, plus 2 chlorides going to lead chloride, solid, right? So our spectator ion is the nitrate, and we can forget about that. Excuse me, nitrate and the sodium, and we can forget about those. All right, so let's go back to the numbers. And we've got 20 mils of lead nitrate. So we're right here, 20 mils. How many moles is that? Well, 0.02 liters, that's the 20 mils, times 0.4 molar. That's going to give us 0.008 moles of lead 2 plus. All right, good. How many moles of the chloride do we have? All right, well, do this. We've got 60 mils, so 0.06 liters times 0.2 molar, 0.2 molar. Okay, that means we've got 0.012 moles of chloride ion. All right, so let me put boxes around that. So at first glance, you'd say, well, they're not equal amounts. In fact, it looks like the lead is the limiting reactant because we have less of it. But you got to keep in mind this coefficient. Right? So remember, it says for every 1 mole of lead chloride or lead, we need 2 moles of sodium chloride. So what that means is if we had enough chloride, we need 0.016 moles. So need chloride. We don't have it, so our chloride is our limiting reactant. Okay, so now we got to base our answer. In other words, the question was how much of the precipitate are we going to form? We base our calculations on the limiting reactant. All right, so let me erase some of this. Okay, so we said, what did we say? 0.012 moles of chloride. All right. Now we still got to look at the balanced equation. For every 2 moles of chloride, we produce 1 mole of lead chloride. So we're going to produce, I'll write this down, produce 0.006 moles of lead chloride solid. And you could have figured that out just by using your mole ratios. Let me do that real quick. 0.012 moles chloride times, okay, 2 moles chloride over 1 mole lead chloride. Okay, so there's our mole ratio. Right? We got that from these 2 coefficients. So that's going to give us the 0.06 moles of lead chloride. Okay, we're almost there. We've got the formula weight. All we do is multiply. Let me back out of this a little bit here. Okay, we're going to produce 0.00006 moles of lead chloride, okay, times 278.11 grams per mole. And that's going to give us, what's our answer here? 1.67 grams of lead chloride in my solution. All right. So that was a fairly lengthy one, but it was a good one because to remind you about making sure your equation is balanced. Oftentimes in a test you'll be told if it's balanced or not. Being aware of limiting reactant issues. Okay. All right. The final, by the way, if you're following along in your book, this is what I've been talking about with the solution stoichiometry, chemical analysis, is chapter 4, I believe, section 6. Yes, section 6. All right. I'm going to talk to you about titrations. Titrations, what are titrations? We're going to go through this fairly quickly. You'll hit it a lot more in depth when you take second semester Gen Chem. So titration is actually a technique that's used in the lab for determining the concentration of an unknown solution. Okay, and this is showing a picture of a typical acid-base titration. In other words, there's a solution in this long, skinny thing. That's your burette. You control the drops by the little stopcock. Here's your unknown solution in here. This is sort of a flow chart. You'll have something similar to this in your book. What's important here is that how do you figure out the concentration of an unknown solution? Well, you need a known solution to add to that. In other words, in this case, let's see, known concentration in the burette, okay, and then unknown in flask, okay. So how does that help us? Well, if we know the concentration of one solution and we add it to the unknown to get a complete reaction. What do I mean by complete reaction? Well, that depends on the type of reaction. We're only going to show you one scenario, and that's acid-base titration. But you should be sort of remember this from the acid-base discussion in a previous chapter. Remember we talked about acid-base neutralization. So for a strong acid, strong base, remember what that was. The net ionic equation gives us this, right? Acid, base, okay, H2O. For a titration, when the reaction is complete, we say it's at the equivalence point. What do we mean by that? That means this. The moles of acidic hydrogen are going to be exactly equal to the moles of base. So in our previous picture, let's say we know the concentration, know sodium hydroxide concentration. Remember, square brackets means moles per liter. Okay? And if we add a certain volume of that to the unknown HCl and to the equivalence point, which we're not going to talk about how you determine that, just we'll say equivalence point is what you're shooting for, then we can figure out the concentration of the HCl. All right. Okay. Here's one example, and this is all we're going to go through. All right. What is the molarity of a hydrochloric acid solution if it took 15 mils of a 0.2 molar sodium hydroxide solution to completely neutralize 20 mils of the HCl solution? What does neutralize? What do we mean by neutralize is this. I've got an acid, and I'm going to neutralize it with a base. And we say neutralize because you fix water, or you produce water. That's neutralization. So the equivalence point means this. The moles of H plus equal moles of OH. All right. So in that previous picture, I guess the way to envision it is this. I've got my flask, and here I've got my volume. This is 20 mils of question mark molarity HCl, and then in my burette, this is my burette picture here, I'm going to add dropwise a 0.2 molar sodium hydroxide solution. And in fact, you're told that you reach the equivalence point when we've added 15 mils of this. All right, let me erase this and just tell you this. So how many moles of hydroxide have we added? Well, we know that. Okay? It's going to be 0.015 liters, all right, times 0.2 molar hydroxide, right? Remember when I say 0.2 molar hydroxide, when we say 0.2 molar sodium hydroxide, that means that solution with respect to this sodium cation is also 0.2 molar, and with respect to the hydroxide ion is also 0.2 molar. And we can ignore the sodium in this case because it's a spectator ion, where all we care about is the hydroxide. Okay, so we have added that many moles of hydroxide. What is that going to be? Well, it's going to be 0.003 moles of hydroxide added. All right. So what do we say about the equivalence point? We said that the moles of the OH equal the moles of the H+. So all we got to do is this. 0.003 moles of H+, but we now divide that by the original volume. Okay, what was that? Well, it's 20 mils, or 0.02 liters HCl solution. Okay, that's it. There's your molarity. Turns out that is, I got it written down here, 0.15 molar. So one more time. In our original flask, we had the 20 mils of the HCl with a question mark molarity. We now know that that's 0.15 molar HCl. All right. Let me, I'm not going to do this, but I'm going to throw some other numbers at you to test yourself. So let me put these down. Try this with, instead of making sodium hydroxide, 15 mils of 0.2 molar barium hydroxide. Why do I do that? Well, think about this. 0.2 molar barium hydroxide is actually, with respect to hydroxide, is equal to 0.4 molar. Okay, so that throws a little twist in at you. If you do that correctly, you should get HCl concentrations 0.3 molar. Or how about this one? Try in our flask, instead of HCl, 20 mils of sulfuric acid. Right? So in other words, let's see here, 20 mils of HCl, make the HCl sulfuric acid. Now, sulfuric acid is a diprotic acid, means it supplies 2 protons per molecule of H2SO4. So in effect, we can say the proton concentration is equal to, what do we say? Excuse me, backwards. You'll have to take that into account when you do your division. So that's all I'll say. I just want to throw these out. I give you the answers here so you can check yourself on this. I think that's all we're going to do on titrations. Yes.